Hello. Welcome. I'm glad you're here. If you've arrived feeling tired, that's perfectly all right. If your mind is still turning over the day, replaying moments, or worrying quietly about tomorrow, you can let that be. You don't need to do anything right now except rest. You don't need to solve anything, finish anything, or even stay awake. This is a place where you can simply be still. Tonight, I'd like to talk with you about something so ordinary, so ever-present, that we rarely stop to consider it at all. I want to tell you about dust, about the tiny drifting particles that fill the air around you, that settle on surfaces, that catch the light when it slants through a window. I want to share with you the quiet, beautiful facts about these microscopic travelers, facts that might help you see the world a little differently, a little more gently. There's something deeply calming about dust once you begin to understand it. It asks nothing of us. It simply exists, drifting slowly through the air, part of an ancient cycle that connects your bedroom to distant stars, your breath to the breath of forests, your home to the vast, patient processes of the earth itself. If you'd like to follow along on more journeys like this one, you're welcome to, but there's no pressure. The only thing that matters right now is that you're comfortable, that you're breathing slowly, and that you're ready to drift into a world of small wonders. So let's begin. Let's step softly into the invisible realm of dust and microscopic particles and discover just how remarkable, how soothing, and how surprisingly beautiful the smallest things can be. Take a slow breath, and let's start with something simple. Every room you've ever been in, every space you've ever occupied, is filled with particles floating through the air. Right now, as you rest, millions upon millions of tiny specks are drifting around you, moving in currents you cannot see. They rise with the warmth of your body. They settle when the air grows still. They are so small that they obey laws of motion quite different from the objects we're used to. They don't fall quickly. They don't crash down. Instead, they float, they hover, they drift like snow that never quite reaches the ground. This gentle suspension is one of the most calming facts about dust. It is almost weightless in its world, moving through air as if through a thick, invisible sea. Most of these particles are far too small to see individually. A single speck of household dust might measure between 1 and 100 micrometers across. To give you a sense of scale, a human hair is about 70 micrometers wide. So many of the particles floating around you right now are smaller than the width of a single hair. They are at the very edge of visibility, inhabitants of a realm that exists between the seen and the unseen. When you notice dust only when it gathers, when it becomes a soft layer on a table or a bookshelf, you're seeing not individual travelers, but whole communities of them, countless specks that have finally come to rest together. And what are these particles made of? The answer is wonderfully varied, a mixture of the world itself. Some dust is mineral, tiny fragments of rock and soil carried on the wind. Some is organic, flakes of your own skin, fibers from fabric, pollen from flowers, spores from fungi. Some comes from farther away than you might imagine. Dust can travel across oceans. It can cross continents. Particles that began their journey in the Sahara Desert can drift all the way across the Atlantic and settle softly in the Amazon rainforest, bringing with them minerals that nourish the soil. Right now, in the air around you, there may be particles that have traveled hundreds or even thousands of miles, each one carrying a tiny piece of somewhere else. Your own body contributes to the dust around you in the gentlest possible way. Every day, you shed millions of skin cells. This is not something to worry about. It's simply part of being alive. Your skin renews itself constantly, quietly, replacing old cells with new ones. The old cells flake away, so small and light that you never notice. They become part of the air, part of the dust, drifting and settling. In a typical home, a significant portion of dust is made of these shed skin cells. It's a reminder that we are not separate from our environment. We are always, gently, becoming part of the world around us, contributing our own microscopic pieces to the great, slow mixture of matter that fills every space. There is something comforting in knowing that dust is, in part, a record of presence. The dust in your home contains traces of everyone who lives there, everyone who visits, even the pets who curl up on the furniture. It holds fragments of the meals you've cooked, the flowers you brought inside, the earth you've tracked in on your shoes. It is a soft, unintended archive, a collection of moments and materials too small to see, but real nonetheless. Dust doesn't judge. It simply gathers, quietly, without urgency. When light streams through a window and you see those bright, drifting specks in the beam, you're witnessing something called the Tyndall effect. The particles in the air scatter the light, making the invisible visible for a moment. It's the same principle that makes the sky blue, the same scattering of light by tiny things suspended in a medium. In that shaft of sunlight, you're seeing proof of the constant, gentle motion that fills the air. Even when a room seems perfectly still, the air is alive with movement, with particles rising and falling, swirling in currents created by warmth and breath and the simple act of being. Dust moves slowly, and that slowness is part of its calming nature. A particle of dust doesn't plummet, it drifts. This is because of something called air resistance, or drag. For objects as small and light as dust particles, air is not a thin, insubstantial gas. It's more like a thick fluid, something they must push through, something that pushes back. The smaller the particle, the more significant this effect becomes. A speck of dust falls through air the way a pebble might sink through honey, slowly, gently, taking its time. Some particles are so small that they barely fall at all. They can remain suspended in the air for hours, even days, drifting on the tiniest currents, traveling wherever the air takes them. This slow motion is why dust can travel so far. Once a particle is lifted into the air, whether by wind, by movement, or by the simple act of walking across a room, it doesn't rush back down. It lingers. It floats. And while it floats, it can be carried. Air currents can lift it higher, carry it through doorways, out windows, across fields and forests. The atmosphere becomes a highway for these microscopic travelers, a vast, invisible network of currents and flows that can transport particles across the globe. It's a patient process, unhurried, taking place on timescales that have nothing to do with human urgency. Let's consider the dust that comes from farther away, from beyond your home, beyond your town. Every year, hundreds of millions of tons of dust are lifted into the atmosphere from deserts around the world. The Sahara alone sends out enormous plumes of dust, clouds of fine particles that drift westward over the Atlantic Ocean. Scientists can track these plumes from satellites, watching as the dust moves in great, slow rivers of air. Some of this dust falls into the ocean, where it provides nutrients like iron to marine life. Some of it reaches South America, settling in the Amazon basin, where it helps replenish nutrients in the rainforest soil. It's a beautiful connection, a reminder that the Earth is not a collection of separate places, but a single, interconnected system, where even the smallest particles play a role in the largest cycles. Dust from the Gobi Desert in Asia can travel across the Pacific Ocean, reaching North America. Dust from the Australian outback can drift over the ocean and affect air quality in New Zealand. These journeys can take days or weeks, with particles floating high in the atmosphere, riding the jet streams, those fast-moving rivers of air that circle the planet. Up there, in the upper reaches of the troposphere, dust particles can travel vast distances, moving faster than any car or train, yet still drifting, still suspended, still patient. Even closer to home, dust tells stories of connection. The dust on your windowsill might contain pollen from trees in a nearby park, soil from a construction site down the street, salt crystals if you live near the ocean, or soot from distant wildfires. Each particle is a tiny ambassador from somewhere else, a fragment of the world that has found its way to you. There's something quietly poetic about this, the idea that your home is constantly receiving these small visitors, that you're always, in a sense, in contact with distant places. Now let's think smaller still, about the particles that are even tinier than typical household dust. These are called aerosols, and they include things like smoke particles, droplets of water, and particles formed from chemical reactions in the atmosphere. Some aerosols are so small that they're measured in nanometers, billionths of a meter. At this scale, particles behave in ways that seem almost magical. They can remain suspended in the air indefinitely, never settling, always moving. They can travel around the world multiple times before they're finally removed from the atmosphere by rain or by sticking to surfaces. These tiny aerosols play a crucial role in one of the most calming, most beautiful processes on Earth, the formation of clouds. For a cloud to form, water vapor in the air needs something to condense onto. It needs a surface, a seed. Dust and aerosol particles provide that surface. High in the atmosphere, water vapor gathers around these microscopic particles, forming tiny droplets. Billions upon billions of these droplets come together, and we see them as clouds, those soft, drifting shapes that cross the sky. Without dust, without these tiny particles, clouds would be far less common. The sky would be a different place. So every time you look up and see clouds, you're seeing the work of dust, the way these smallest fragments of matter help shape the weather, the climate, the very appearance of the world. This role in cloud formation means that dust has a subtle but real effect on the Earth's temperature. Clouds reflect sunlight back into space, cooling the planet. They also trap heat radiating from the Earth's surface, warming it. The balance between these effects depends, in part, on the number and type of particles in the atmosphere. Dust, then, is part of the Earth's climate system, a quiet participant in the vast, slow processes that keep our planet habitable. It's humbling to think that something so small, so easy to overlook, is woven into systems so large and so essential. Let's return to your immediate surroundings, to the dust that settles on surfaces. There's a reason dust accumulates, a reason it seems to reappear no matter how often you clean. It's because the process never stops. Particles are always drifting, always settling. They land softly, without sound, without force. Over time, they build up, layer by layer, creating that familiar soft coating. But here's a calming thought. Dust settles slowly. It's not an invasion. It's not a failure. It's simply the natural result of living in a world filled with particles, a world where matter is constantly moving, constantly redistributing itself. Dust is patient. It will wait. And when it settles, it does so gently, without harm. The texture of settled dust is surprisingly delicate. If you were to look at it under a microscope, you'd see a landscape of varied shapes and sizes. Some particles are perfectly round, smooth spheres. Others are jagged, irregular, like tiny shards of glass. Some are long and fibrous, threads from fabric or plant material. Some are flat flakes, like the skin cells we mentioned earlier. Together, they create a loose, airy structure full of empty space. This is why dust is so soft, so easily disturbed. It's not packed tightly. It's a loose assembly, a community of particles resting together, barely touching. This loose structure also means that dust can hold on to other things. It can trap moisture from the air, which is why dust in humid environments can feel slightly damp or sticky. It can hold on to odors, absorbing molecules from cooking, from smoke, from perfumes. It can even harbor tiny living things, like dust mites, those microscopic creatures that live their entire lives in the landscape of settled dust, feeding on shed skin cells. Dust mites are so small that you'd need a microscope to see one clearly, and they're completely harmless to most people. Just another part of the hidden ecosystem that exists in every home. Speaking of ecosystems, let's think about dust outdoors in natural environments. In forests, dust includes particles of pollen, spores from mosses and ferns, fragments of leaves and bark, tiny insects, and even bacteria. These particles drift through the forest air, settling on leaves, on the ground, becoming part of the soil. In deserts, dust is mostly mineral, fine particles of sand and clay, shaped by wind and time. In cities, dust includes all of these natural components plus particles from human activity. Brake dust from cars, particles from construction, soot from combustion. Each environment has its own signature mixture, its own particular blend of particles that reflect the character of the place. One of the most remarkable things about dust is its age. Some particles are freshly created, like a flake of skin that left your body today, or a grain of pollen released this morning. But other particles are ancient. Mineral dust, the tiny fragments of rock that blow off deserts and dry landscapes, can be millions of years old. The rock itself formed long ago, deep in the earth or on its surface, and over time, weathering and erosion have broken it down into smaller and smaller pieces. The particle that drifts past your window today might be a fragment of a mountain that stood tall when dinosaurs walked the earth. It has been traveling in one form or another for an unimaginable span of time, and now, for this brief moment, it shares the air with you. Even more ancient are the particles that come from space. Every day, the Earth is showered with micrometeorites, tiny fragments of asteroids and comets that burn up as they enter the atmosphere. Most of these are so small that they don't create the bright streaks we call shooting stars. Instead, they drift down slowly, adding to the dust on Earth's surface. Scientists estimate that tens of thousands of tons of this cosmic dust settle on Earth every year. It's a gentle, constant rain of material from space, so fine and so dispersed that we never notice it. But it's there, mixing with terrestrial dust, becoming part of the soil, part of the ocean, part of the air we breathe. You are, in a very real sense, surrounded by stardust, by particles that were once part of the early solar system, that have traveled through space for billions of years before finally coming to rest here. This cosmic dust is ancient in a different way than old rock. It formed in the early solar system over 4.5 billion years ago, when the sun and planets were just beginning to take shape. Some of it may even predate the solar system, having formed in other stars and been scattered into space when those stars died. These particles carry with them a record of deep time, of processes and events that happened long before the Earth existed. When scientists study cosmic dust, they're studying the raw materials of planets, the building blocks of worlds. And some of that material is here, now, drifting invisibly around you. Let's shift our focus to the way dust interacts with light, because this is where some of the most beautiful and calming effects occur. We've already mentioned the way particles scatter light, making a sunbeam visible. But dust also affects the color of light. When the sun is low on the horizon, at sunrise or sunset, its light has to pass through a much thicker layer of atmosphere to reach you. Along the way, it encounters countless particles, dust and aerosols suspended in the air. These particles scatter the shorter wavelengths of light, the blues and violets, in all directions. What's left to reach your eyes are the longer wavelengths, the reds and oranges and pinks. This is why sunsets are so often brilliantly colored. Dust, in a sense, paints the sky. The more particles in the air, the more vivid the colors can be. After a volcanic eruption, when the atmosphere is filled with fine ash, sunsets around the world can become extraordinarily vibrant, glowing with colors that seem almost unreal. Even the simple blue of the daytime sky is influenced by particles. While most of the scattering that makes the sky blue is done by air molecules themselves, dust and aerosols contribute as well, adding depth and variation to the color. On a perfectly clear day, with very little dust, the sky can be a deep, pure blue. On a hazy day, when there's more dust or pollution, the sky can appear paler, more washed out. The sky, then, is not just empty space above us. It's a canvas on which dust and light collaborate to create the colors we see, a constantly changing display that depends on the invisible particles drifting through the air. Dust also plays a role in the soft, diffused light you experience on a cloudy day. Clouds scatter light in all directions, creating a gentle, even illumination with no harsh shadows. This is light that has interacted with countless water droplets and particles, bouncing and scattering until it reaches you from every angle. It's a calming kind of light, the kind that feels restful to the eyes, that makes colors appear soft and muted. And it all begins with dust, with those tiny particles that gave the water vapor something to condense onto, that helped the clouds form in the first place. There's a phenomenon called the blue hour, that brief period of twilight after the sun has set, but before full darkness falls. During this time, the sky takes on a deep, serene blue, a color that feels peaceful and contemplative. This color is created by the scattering of light by the atmosphere, including its particles. The sun is below the horizon, but its light still reaches the upper atmosphere, where it's scattered by air molecules and dust. The result is that beautiful, even glow, a light that seems to come from everywhere and nowhere, that wraps the world in a soft, blue calm. Dust, in its quiet way, is part of creating this moment, this transition from day to night. Now, let's think about the way dust settles, the actual process by which particles come to rest. It's governed by gravity, of course, but also by air currents, by static electricity, and by the shape and size of the particles themselves. Larger, heavier particles settle faster. Smaller, lighter ones can remain airborne almost indefinitely. When air is perfectly still, particles will slowly drift downward, but perfect stillness is rare. There's almost always some movement, some current, created by temperature differences, by the movement of people or animals, by wind coming through a window. So particles don't fall straight down. They swirl, they eddy, they take long, wandering paths through the air before finally coming to rest. Static electricity plays a surprising role in where dust settles. Particles can pick up an electric charge as they move through the air, rubbing against other particles or against surfaces. Once charged, they're attracted to surfaces with the opposite charge, or they may be repelled by surfaces with the same charge. This is why dust often accumulates on television screens and computer monitors, which can build up static charges. It's also why dust can cling to certain surfaces more than others, why it might gather on a plastic surface more readily than on wood. The invisible forces of electricity are at work, gently pulling particles out of the air and onto surfaces. When dust lands on a surface, it doesn't just sit there passively. It can be disturbed and lifted back into the air by the slightest breeze, by footsteps, by opening a door. This is called resuspension, and it means that dust is constantly cycling between being airborne and being settled. A particle might settle on a table, rest there for a few hours or days, then be lifted back into the air by someone walking past. It might drift to another part of the room, settle again, be lifted again. Over time, a single particle can travel throughout a house, visiting every room, every surface in a slow, aimless journey. There's something almost whimsical about this, the idea of dust as tiny, accidental travelers, moving through our spaces without intention or destination. Let's consider the dust that accumulates in hidden places, in the corners of rooms, under furniture, on top of high shelves. These are the places where air currents are weakest, where particles can settle and remain undisturbed for long periods. Over time, the dust in these places can become thick, forming soft, gray layers or even clumps. These accumulations are sometimes called dust bunnies, a gentle, playful name for something that's really just a collection of fibers and particles that have tangled together. Dust bunnies form because the particles aren't just settling. They're also sticking to each other, held together by static electricity, by moisture, by the natural tendency of fibers to intertwine. They're harmless, just another small, quiet feature of the hidden landscape of a home. In nature, dust accumulates in different ways. In deserts, it can gather in the lee of rocks or plants, forming small drifts. In forests, it settles on leaves and eventually gets washed off by rain, carrying nutrients down to the soil. In the ocean, dust that has traveled across the atmosphere settles onto the water surface, where it can be taken up by plankton or sinks slowly to the ocean floor. Over millions of years, layers of settled dust can build up on the seafloor, compressing into rock, becoming part of the geological record. Scientists study these layers to learn about past climates, about ancient wind patterns, about the conditions on Earth long ago. Dust, then, is not just a feature of the present. It's a link to the past, a way of reading history written in particles. There's a type of dust called loess, which is wind-deposited silt that accumulates over time into thick layers. In some parts of the world, loess deposits can be hundreds of feet thick, representing millions of years of dust settling from the air. These deposits are incredibly fertile, making excellent farmland. The great agricultural regions of China, the central United States, and parts of Europe are built on loess. It's dust that has become soil, that now supports crops and forests and human communities. It's a reminder that dust is not waste, not something to be merely cleaned away. It's raw material, the substance from which new things are built. Let's turn our attention to the particles in the air you're breathing right now. With every breath, you inhale thousands, perhaps millions of particles. Most of them are completely harmless. Your respiratory system is designed to handle them. The nose and throat filter out larger particles. Tiny hairs called cilia, along with mucus, trap particles and move them out of the airways. Smaller particles that reach the lungs are dealt with by immune cells, which engulf and remove them. It's a quiet, constant process, one that happens without you ever having to think about it. Your body knows how to coexist with dust, how to live in a world where the air is never perfectly clean. The air you breathe has always contained particles. Our ancestors breathed air filled with dust from the savanna, with smoke from fires, with pollen and spores. Our bodies evolved in this environment, adapting to the presence of particles. In a sense, we're designed to live with dust, to filter it, to tolerate it. The idea of perfectly clean air, air with no particles at all, is not only impossible, but also unnecessary. A certain amount of dust is simply part of the atmosphere, part of the natural world, and our bodies are perfectly capable of handling it. There's even some evidence that exposure to a variety of particles, especially in childhood, can help train the immune system, making it more balanced and less likely to overreact to harmless substances. This is sometimes called the hygiene hypothesis, the idea that growing up in an environment that's too clean, too sterile, might actually increase the risk of allergies and asthma. While the science is still being explored, it suggests that a little dust, a little exposure to the microbial and particulate diversity of the world might be beneficial. It's a reminder not to fear dust, not to see it as an enemy, but simply as part of the environment we live in. Of course, not all particles are benign. Some, like those from pollution or from certain molds, can be harmful in high concentrations. But typical household dust, the kind we're talking about tonight, is generally harmless. It's a mixture of natural and human-made materials, most of which pose no threat. The key is balance, is perspective. Dust is not something to obsess over, not something to wage war against. It's simply there, a quiet, constant presence, and understanding it can help us feel more at ease with it. Let's think about the way dust moves through a home over the course of a day. In the morning, when people wake and begin moving around, dust is stirred up, lifted into the air by footsteps, by opening doors, by the bustle of activity. The air becomes filled with particles, though you can't see them unless light catches them just right. As the day goes on, as people leave and the house becomes still, the dust begins to settle again, drifting slowly downward, coming to rest on surfaces. By evening, the air might be clearer, the particles having settled. Then, as people return, the cycle begins again. It's a gentle rhythm, a daily dance of disturbance and settling, of movement and rest. Temperature also affects how dust moves. Warm air rises, carrying particles with it. Cool air sinks, bringing particles down. In a room with a heater or a sunny window, you can have convection currents, loops of air that circulate, carrying dust around the room. A particle might be lifted by warm air near the heater, drift across the ceiling, cool, and descend on the other side of the room, then be pulled back toward the heater by the flow of air along the floor. It's a slow, lazy circulation, invisible but constant, part of the hidden life of a room. Humidity affects dust as well. In dry air, particles remain light and easily airborne. In humid air, they can absorb moisture, becoming slightly heavier, more likely to settle. This is why dust can seem more noticeable in dry climates or during winter when indoor air is heated and dried out. It's also why a bit of humidity can help keep dust down, making particles settle more readily. The air itself is part of the story, its temperature and moisture content shaping the behavior of the particles it holds. Let's consider the dust that gathers on plants, both indoors and outdoors. Leaves can become coated with a fine layer of dust, which can actually affect the plant's ability to photosynthesize by blocking light. In nature, rain washes this dust away, keeping leaves clean. For houseplants, you can gently wipe the leaves with a damp cloth, helping the plant breathe and absorb light more effectively. It's a small act of care, a way of acknowledging that dust affects not just us, but all living things, and that sometimes a little attention, a little cleaning, is a kindness. Outdoors, dust on leaves can tell you something about the environment. In a city, leaves might be coated with a dark layer of soot and pollution particles. In a rural area, the dust might be lighter, more mineral-based, perhaps mixed with pollen. Near the ocean, leaves might have a slight salty residue from sea spray. Each environment leaves its signature, its particular blend of particles, on the surfaces around it. There's a certain beauty in the way dust reveals air currents. If you've ever seen dust swirling in a shaft of sunlight, you've seen the air itself made visible. The particles trace the flow of air, showing you eddies and currents that would otherwise be invisible. It's a reminder that the air around you is not static. It's always moving, always flowing, shaped by temperature, by wind, by the movement of objects and bodies. Dust is the messenger, the visible sign of this invisible motion. In some traditions, dust is seen as a symbol of humility, of the transient nature of life. Dust to dust. The saying goes, acknowledging that all material things eventually break down, return to the earth, become part of the great cycle of matter. There's a certain peace in this idea, a reminder that nothing is permanent, that everything is part of a larger process. Dust is not an ending, but a transformation, a stage in the ongoing journey of matter through the world. Scientists who study dust, who collect it and analyze it, find stories in every sample. Dust from the Arctic contains particles from industrial regions thousands of miles away, carried by wind and weather. Dust from the deep ocean floor contains micrometeorites and the remains of ancient plankton. Dust from your attic might contain fibers from clothing worn decades ago, fragments of materials that are no longer made. Each particle is a tiny piece of evidence, a clue to where it came from, how it traveled, what it has witnessed. Dust is a record, a library written in the smallest possible script. There's something deeply calming about the idea that dust connects us to the rest of the world, to distant places and distant times. The air you breathe, the surfaces around you, are in constant, gentle communication with the larger Earth, receiving particles from afar, sending particles out. You are not isolated. You are part of a vast, slow exchange of matter, a participant in cycles that span the globe and reach back through deep time. And dust, humble and overlooked, is the medium of this connection. As you rest tonight, as you let your mind settle like dust in still air, you can take comfort in these facts. Dust is not something to fear or fight. It's simply part of the world, part of the atmosphere, part of the story of matter and motion that surrounds us all. It drifts, it settles, it rises again, in a cycle that is as natural as breathing, as constant as the turning of the earth. And in understanding it, in seeing it not as dirt, but as a collection of travelers, of fragments, of tiny pieces of the world, you can find a kind of peace. Deep within every household, there exists a remarkable library of information written in the language of dust. Each particle carries a signature, a tiny fingerprint of where it came from and what it has touched. Scientists have learned to read these signatures, discovering stories that span continents and centuries, all preserved in the gentlest archive imaginable. The dust beneath your bed holds traces of volcanic eruptions from decades ago, pollen from flowers that bloomed last spring, and minerals that once rested in mountain ranges now worn smooth by time. This silent record asks nothing of you, simply accumulating its knowledge while you sleep, while you dream, while you live your life in the rooms above. The way dust settles follows patterns so consistent that they border on mathematical poetry. Larger particles descend more quickly, obeying the simple pull of gravity with straightforward honesty. Smaller particles drift and wander, taking hours or even days to complete their gentle journey downward. The very smallest ones, those measuring just a few micrometers across, may never settle at all in a room with even the slightest air movement. They remain suspended indefinitely, floating citizens of the air, moving in currents too subtle for human senses to detect. This creates invisible layers in every room, with the heaviest particles below and the lightest ones drifting near the ceiling, a vertical geography of matter that reorganizes itself with every opening of a door, every footstep, every breath. When sunlight passes through a window and illuminates a beam of floating dust, you are witnessing something called the Tyndall effect. This phenomenon occurs when light scatters off particles that are suspended in a medium, making the beam itself visible rather than just the surfaces it touches. The same effect makes clouds visible in the sky and gives fog its ghostly appearance. Each dust particle in that sunbeam acts as a tiny mirror, bouncing photons in new directions, creating a luminous path through the air. Without these particles, the light would pass invisibly through the room, noticed only when it struck a wall or floor. The dust, in its own quiet way, reveals the light itself, making the invisible visible, turning empty air into something you can almost touch with your eyes. Dust particles in your home have traveled remarkable distances to reach you. Saharan dust, lifted by strong winds over the African desert, regularly crosses the Atlantic Ocean, carried on high-altitude air currents for thousands of miles. Some of it settles in the Amazon rainforest, delivering nutrients that the jungle needs to thrive. Some of it continues onward, eventually drifting down through the atmosphere to land on windowsills in North America, Europe, and beyond. The same air that moves above the ocean carries dust from Asian deserts to the Pacific Islands, from Australian outback to Antarctic ice. In this way, every continent shares its substance with every other, and the dust in your room may have begun its journey in a place you have never seen, a landscape you have never imagined, now resting quietly beside you as you rest. The composition of household dust varies beautifully from room to room, creating unique signatures for each space you inhabit. In a bedroom, you will find a higher concentration of skin cells, textile fibers from bedding and clothing, and the microscopic remnants of personal care products. In a kitchen, dust contains more food particles, cooking oils that have condensed and dried, and minerals from tap water that has evaporated. A living room accumulates paper fibers from books and magazines, particles from shoe soles that have tracked outdoor soil inside, and if you have pets, an abundance of hair and dander. Each room tells its own story through its dust, a gentle autobiography written in matter too small to see individually, but present in quantities that eventually become visible. Cosmic dust, the particles that drift through space between stars, share surprising similarities with the dust in your home. Both contain silicates, tiny fragments of silicon and oxygen bonded together in crystalline structures. Both contain carbon in various forms, from simple molecules to complex organic compounds. The main difference lies in their journey and their age. Cosmic dust was formed in the atmospheres of dying stars, blown outward by stellar winds, then scattered through the galaxy over millions or billions of years. Some of this ancient dust eventually fell to Earth, becoming part of the planet's substance. And through countless transformations, some fraction of it may now rest in your home, indistinguishable from younger dust, but carrying within its atomic structure a history that predates human civilization, predates life itself, predates even the formation of our world. The human body sheds approximately 30 to 40,000 skin cells every minute. These cells, each one a complete biological structure that once formed part of your protective outer layer, become airborne and join the floating population of household dust. This is not a process to fear or find unsettling, but rather a normal, healthy, and continuous renewal. Your skin replaces itself entirely about every 28 days, shedding the old to make way for the new. The cells that drift away from you have served their purpose, protecting you from the environment, and now they simply return to that environment in the gentlest possible way. They settle on surfaces, mix with other particles, and eventually are swept away or vacuumed up, making room for tomorrow's contribution. In this way, you are always leaving a little of yourself behind, a soft trace of your presence in every place you spend time. Dust mites, the tiny creatures that live in household dust, are often mentioned with alarm, but they deserve a calmer consideration. These microscopic relatives of spiders and ticks measure about 1/4 of a millimeter in length, far too small to see without magnification, and they live their entire lives in the comfortable environments we create in our homes. They feed primarily on the skin cells that humans shed, making them nature's recyclers, quietly processing the biological material we leave behind. A typical mattress might contain anywhere from 100,000 to 10 million dust mites, a number that sounds dramatic until you remember that you never see them, never feel them, and in most cases, never experience any effect from their presence. They live their small lives without interfering with yours, asking only for the warmth and humidity that you yourself prefer, turning your shed cells back into simpler compounds that eventually break down completely. The movement of dust through a room follows the same fluid dynamics that govern the movement of water in a stream or air around an airplane wing. When you walk across a room, you create a pressure wave that pushes air ahead of you and pulls it along behind, setting up complex swirling patterns called vortices. These vortices lift dust from the floor and carry it along in your wake, redistributing particles throughout the space. When you sit down, the air you displace continues to move for several minutes, gradually settling into stillness as friction and viscosity dissipate the energy you introduced. Opening a door creates a pressure difference between rooms, causing air to flow from high pressure to low pressure, carrying dust along with it. Every action you take in a space creates invisible currents, and dust, being light and easily moved, rides these currents like leaves on a stream, never fighting, always yielding, eventually coming to rest in new locations where it waits patiently for the next disturbance. In the upper atmosphere, about 50 to 80 kilometers above the Earth's surface, there exists a layer of dust so fine and so high that it never settles to the ground. This dust, delivered by meteors that burn up as they enter the atmosphere, remains suspended for years or even decades, slowly drifting eastward in the mesospheric winds. These particles are smaller than a micrometer, so tiny that air molecules buffet them constantly, keeping them aloft despite gravity's pull. They serve as nucleation sites for rare clouds called noctilucent clouds, which form in the cold mesosphere during summer months at high latitudes. These clouds glow with a soft blue light after sunset, visible only when the sun has dipped below the horizon, but still illuminates the high atmosphere. The dust that enables these clouds to form came from space, from comets and asteroids that shed material as they pass through the inner solar system. And now that material creates beauty in Earth's sky, a gift from the cosmos that asks nothing in return. The color of dust varies depending on its composition, and this variation tells stories about the environment it came from. Desert dust tends toward reds, oranges, and browns, colored by iron oxides that form when iron-bearing minerals weather in dry conditions. Volcanic dust often appears gray or black, rich in basaltic minerals and volcanic glass. Dust from limestone regions takes on pale cream or white tones, reflecting the calcium carbonate that makes up the rock. In industrial areas, dust may contain carbon soot that darkens it, while in agricultural regions, it carries the golden tones of dried plant matter and soil organic material. The dust in your home blends all these colors together, creating the neutral gray or beige that we associate with settled dust. A mixture so complete that no single component dominates. A democracy of particles where every origin has equal representation. Dust plays a crucial role in the formation of raindrops, a role so essential that without it, rain as we know it would be impossible. Water vapor in the atmosphere needs something to condense onto a solid surface where the first tiny droplets can form. Dust particles, along with other aerosols like sea salt and pollen, provide these surfaces. A water molecule in the air will bounce around randomly until it encounters a dust particle, where it can stick and be joined by other water molecules, gradually building up a droplet large enough to reflect light and become visible as part of a cloud. Without dust and other particles serving as these condensation nuclei, water vapor would remain in gaseous form, even in very humid conditions, and clouds would not form. The dust in the air, then, is not just a passive presence, but an active participant in the water cycle, helping to create the rain that nourishes all terrestrial life, a humble particle performing an essential service without recognition or reward. In the deep ocean, far from any land, dust settles onto the seafloor in quantities so small that it accumulates at a rate of just millimeters per thousand years. This dust, carried by wind far out over the water and eventually falling through the atmosphere into the sea, then sinks slowly through the water column, taking weeks or months to reach the bottom. Once there, it joins the sediment, mixing with the shells of tiny marine organisms and the occasional larger skeleton. Over millions of years, this mixture compresses into rock, preserving a record of atmospheric conditions, ocean chemistry, and climate patterns. Scientists drill cores from the ocean floor and read this record like a book, finding layers of dust that correspond to ice ages, periods of intense volcanic activity, and times when deserts expanded across continents. The dust that once drifted through ancient skies now rests kilometers below the ocean surface, holding secrets about worlds that existed long before humans walked the earth. The static electricity that builds up on surfaces in your home has an interesting relationship with dust. Dust particles, being small and often irregular in shape, easily acquire electric charges through friction as they move through the air or across surfaces. Once charged, they are attracted to surfaces with opposite charges, which is why dust seems to accumulate preferentially on television screens, computer monitors, and other electronic devices. These devices generate electric fields during operation, and charged dust particles follow the field lines, drawn inexorably toward the screen. The dust doesn't stick because of any adhesive property, but simply because of electromagnetic attraction, one of the fundamental forces of nature operating at the scale of household cleaning. When you wipe the dust away, you are temporarily neutralizing these charges, but they build up again quickly, and the dust returns, patient and persistent, following the invisible architecture of electric fields that permeate your living space. Pollen grains, which form a significant component of outdoor dust during spring and summer, are among the most resilient particles in nature. Each grain is protected by a tough outer wall called the exene, made from one of the most chemically resistant organic materials known. This wall can survive for millions of years under the right conditions, which is why paleobotanists can study ancient pollen preserved in sediments and reconstruct the plant communities that existed in the distant past. When you see pollen dust on your car or windowsill, you're looking at one of nature's most sophisticated delivery systems, each grain containing the male genetic material of a plant, packaged for transport by wind, water, or animals. The dust that makes some people sneeze is actually a vast fleet of tiny vehicles, each one carrying the potential for new life, each one shaped by millions of years of evolution to be light enough to travel far, yet sturdy enough to survive the journey. In indoor environments, dust concentrations typically range from 10 to 100 micrograms per cubic meter of air, though this varies widely depending on ventilation, cleaning practices, and outdoor conditions. To put this in perspective, a microgram is 1/millionth of a gram. So even at the high end of this range, a cubic meter of air, which is about the volume of a large refrigerator, contains only 1/10,000th of a gram of dust. Most of this dust is invisible to the naked eye, and the particles you see floating in a sunbeam represent only the largest fraction of the dust population. The majority of particles are so small that they scatter light poorly and pass through the air unseen, detectable only with specialized instruments. This means that the air you perceive as clean and clear actually contains millions of particles, a hidden population that coexists with you in every breath, every moment, causing no harm, simply sharing the space. The dust on Mars, that distant world that has captured human imagination for centuries, differs from Earth dust in fascinating ways. Martian dust is extremely fine, with particles averaging about 3 micrometers in diameter, about half the size of typical Earth dust. It is also rich in iron oxide, which gives Mars its characteristic red color, the same compound that creates rust on Earth. This dust is lifted by Martian winds and can remain suspended in the thin atmosphere for months, creating planet-wide dust storms that obscure the surface from view. When the dust settles, it covers everything in a fine red layer, coating the rocks, the valleys, the polar caps, creating a landscape of uniform color. Spacecraft that have landed on Mars have watched this dust settle on their solar panels, gradually reducing power generation, a slow and gentle process that eventually ends missions, not through any dramatic failure, but simply through the patient accumulation of microscopic particles, each one contributing its small weight to the total burden. The process of dust formation in your home is continuous and unstoppable, but this is not a problem to be solved, merely a fact to be accepted. Every fabric that experiences friction sheds fibers. Every paper product releases cellulose particles. Every time you cook, tiny droplets of oil become airborne, eventually drying into solid particles. Every time you enter from outside, you bring soil particles on your shoes. Every pet contributes hair and dander. Every plant sheds pollen and plant material. Every human sheds skin. All of these processes are normal, natural, and unavoidable aspects of living in a space. The dust that results is simply the physical evidence of life being lived, of activity, of presence, of existence. Fighting it completely would require living in a sealed clean room, wearing special clothing, breathing filtered air, a sterile existence that would eliminate the dust, but also eliminate much of what makes a house a home. Dust in the interstellar medium, the vast spaces between stars, plays a crucial role in the formation of new stars and planets. These particles, though incredibly sparse by Earth standards, are dense enough in certain regions to begin clumping together under their own gravity. As the clumps grow, they attract more material, eventually forming clouds of gas and dust that span light years. Within these clouds, denser regions collapse further, heating up as they contract, until eventually the pressure and temperature at the core become high enough to ignite nuclear fusion, and a star is born. The remaining dust in the disk around the young star gradually coalesces into larger bodies, first small grains sticking together, then pebbles, then boulders, then planetesimals, and finally planets. The Earth itself, and everything on it, including you, is made from dust that once drifted through interstellar space, brought together by gravity and time into a world capable of supporting life, of generating consciousness, of looking back out at the universe and wondering about its origins. The speed at which a dust particle falls through air depends on its size and shape in ways that seem simple but contain subtle complexity. A spherical particle 1 micrometer in diameter falls at about 0.00004 meters per second, so slowly that it would take about 7 hours to fall 1 meter in perfectly still air. A particle 10 micrometers across falls about 100 times faster at roughly 0.003 meters per second, completing the same 1 meter journey in about 5.5 minutes. A particle 100 micrometers in diameter, just barely visible to the naked eye, falls at about 0.25 meters per second, dropping 1 meter in just 4 seconds. But most dust particles are not spherical, and their irregular shapes create drag that slows their descent, causing them to tumble and spin as they fall, taking longer to reach the ground than a smooth sphere of the same mass would take. This is why dust seems to hang in the air, why it takes so long to settle after you have disturbed it, why the air never seems completely clear. In ancient ice cores drilled from Antarctica and Greenland, scientists find layers of dust preserved in ice that fell as snow hundreds of thousands of years ago. Each layer corresponds to a specific time period, and the amount and type of dust in that layer tells a story about the climate and environment of that era. During ice ages, when much of the world was colder and drier, dust levels in the ice are much higher, indicating that more dust was being blown around by winds sweeping across expanded deserts and exposed continental shelves. During warmer interglacial periods, like the one we are currently in, dust levels are lower, showing that vegetation covered more of the land surface, holding soil in place and preventing it from becoming airborne. By studying these dust layers, scientists can reconstruct changes in wind patterns, temperature, precipitation, and vegetation cover going back nearly 1 million years, all from particles so small that individually they are invisible, but collectively they write a history more detailed than any human record. The dust that accumulates on bookshelves has a particular composition that reflects the nature of books themselves. Paper, especially older paper made from wood pulp, slowly degrades over time, releasing microscopic cellulose fibers into the air. These fibers mix with the usual household dust components, but in a room full of books, they become the dominant fraction. If you have ever noticed that bookshelves seem to accumulate dust more quickly than other surfaces, this is partly because the books themselves are contributing to that dust, slowly releasing their substance into the air around them. This is not harmful to you or to the books, just a normal consequence of having organic materials in your environment. The dust on your books is, in a very real sense, made partly from the books themselves, a gentle reminder that all physical things are temporary. All solid objects are slowly returning to dust. Though the process is so slow that a book will remain readable for centuries, the loss of material is so gradual that it is imperceptible except through the dust it leaves behind. Dust particles can carry microorganisms, bacteria, and fungal spores that travel through the air attached to larger particles. This might sound concerning, but it is actually a normal and generally harmless aspect of the microbial world that surrounds us always. The vast majority of these microorganisms are benign, and many are beneficial, part of the complex ecosystem that exists in every human environment. Your home contains thousands of species of bacteria and hundreds of species of fungi, most of which you will never notice and which will never affect you in any way. They live on surfaces, in dust, in the air, cycling nutrients, breaking down organic matter, competing with each other for resources, forming a miniature world that exists alongside your own. Some of these microorganisms came from outside, carried in on dust. Some came from your own body, as humans shed not just skin cells, but also the bacteria that live on skin. Some came from your pets, your plants, your food. Together they form a community, a microbiome of your home, unique to your space and reflecting the life you live within it. The optical phenomenon that makes distant mountains appear blue, called atmospheric perspective or aerial perspective, is caused by dust and other particles in the atmosphere scattering sunlight. When you look at something nearby, the light that reaches your eyes has traveled through only a short distance of air, and relatively few photons have been scattered away from the direct path. When you look at something far away, the light has traveled through much more air, and more scattering has occurred. Blue light, having a shorter wavelength, scatters more efficiently than red light. So the scattered light that reaches your eyes from the space between you and the distant mountain is predominantly blue. This is the same reason the sky itself appears blue. The dust and air molecules between you and the distant landscape are acting as a filter, removing direct light and adding scattered blue light, creating the soft blue haze that painters have used for centuries to convey depth and distance. Without dust and air molecules, distant mountains would appear just as sharp and colorful as nearby ones, and the sense of depth that we rely on to judge distance would be diminished. In desert regions, dust storms can lift millions of tons of material into the atmosphere in a single event, creating walls of dust that tower kilometers high and stretch for hundreds of kilometers. These storms, called habubs in some regions, are driven by the downdrafts from thunderstorms, which hit the ground and spread outward, picking up loose soil and carrying it forward at speeds that can exceed 60 kilometers per hour. To be in the path of such a storm is to experience dust not as a gentle presence, but as an overwhelming force, darkening the sky, reducing visibility to zero, penetrating every crack and crevice. Yet even these dramatic events are part of the natural cycle of dust, redistributing soil nutrients, carrying minerals from one place to another, shaping the landscape through erosion and deposition. After the storm passes, the dust settles, sometimes far from where it was lifted, and life continues, adapted to these periodic upheavals, resilient in the face of nature's power. The dust in museums presents special challenges for conservators who work to preserve artifacts and artworks for future generations. Even small amounts of dust can cause damage over time, as particles settle on surfaces and, in the presence of humidity, can promote chemical reactions that degrade materials. Dust can also be abrasive, scratching delicate surfaces when it is wiped away improperly. For these reasons, museums maintain strict climate control, filtering the air to remove particles before they can settle on collections. Display cases are sealed to keep dust out. Galleries are cleaned regularly with specialized equipment that captures dust without spreading it around. Despite all these efforts, dust still finds its way in, patient and persistent, a reminder that no environment can be perfectly controlled, no object perfectly protected from the passage of time. The conservators work with this reality, not against it, accepting that preservation is about slowing change, not stopping it, about giving future generations the best chance to experience the past, while acknowledging that nothing lasts forever. The dust that collects in the corners of rooms, along baseboards and under furniture, forms structures called dust bunnies or dust bunnies, loose aggregations of particles held together by static electricity and the tangling of fibers. These structures can grow surprisingly large, sometimes reaching several centimeters in diameter, visible evidence of the dust that usually remains hidden. They form because air currents in a room tend to move dust along the floor until it encounters an obstacle or a corner where the air flow slows down. There, the dust settles and begins to accumulate, with each new particle adding to the growing structure. Long fibers, like hair and textile threads, act as a framework, and smaller particles fill in the spaces between them. The result is a fluffy, lightweight mass that moves easily when disturbed but otherwise rests quietly in its corner, growing slowly, a small monument to the passage of time and the constant generation of dust in a lived-in space. Dust in the atmosphere affects global temperatures by both reflecting incoming sunlight back to space and absorbing outgoing heat from the Earth's surface. The balance between these two effects depends on the type of dust, its size distribution, and its altitude. Light-colored dust, like that from deserts, tends to reflect more light than it absorbs, creating a cooling effect. Dark dust, like soot from fires, absorbs more light, creating a warming effect. Dust in the upper atmosphere, where it can remain suspended for long periods, has a stronger effect than dust near the surface, which settles out quickly. Volcanic eruptions that inject large amounts of dust and sulfur dioxide into the stratosphere can cool the planet for several years, as the particles spread around the globe and reflect sunlight. The 1991 eruption of Mount Pinatubo, for example, lowered global temperatures by about 0.5 degrees Celsius for 2 years. This shows that dust, despite being composed of tiny particles that individually have no noticeable effect, can collectively influence the climate of an entire planet, a reminder that small things, when present in large numbers, can have profound consequences. The act of sweeping or vacuuming dust is itself an interesting physical process. When you sweep, you use the broom to impart momentum to dust particles, pushing them along the floor and gathering them into a pile. Some particles, especially the smallest ones, become airborne during this process, lifted by the turbulence created by the broom's movement. These airborne particles will eventually resettle, often in places you just cleaned, which is why sweeping never seems to remove all the dust permanently. Vacuuming is more effective because it captures particles in a filter or bag, removing them from the room entirely. But even vacuums release some particles back into the air, especially if their filters are not perfectly efficient. The very finest particles, those smaller than a few micrometers, can pass through many vacuum filters and return to the room, still airborne, still part of the dust population. This is not a failure of cleaning, but simply a recognition that dust is always present, always being generated, and that cleaning is about managing it, reducing it to acceptable levels, not eliminating it completely. In the Arctic and Antarctic, where human activity is minimal and air is often very clean, dust concentrations can be extremely low, sometimes just a few micrograms per cubic meter. This dust comes primarily from long-range transport, carried by winds from distant continents, and from local sources like exposed rock and soil during the brief summer months. The ice sheets themselves are remarkably clean, composed of snow that fell over thousands of years, each layer preserving a sample of the atmosphere at the time it fell. When scientists drill ice cores and melt the ice, they can filter out the dust and analyze it, determining its composition and origin. This dust, so sparse and so carefully preserved, provides evidence of ancient climates, volcanic eruptions, and even human activities like metal smelting and industrial pollution. The cleanest ice on Earth, then, still contains dust, a testament to dust's ubiquity, its ability to travel anywhere, to be present everywhere, a truly global phenomenon that connects all places and all times. The microscopic world of dust reveals itself most beautifully when we consider how particles interact with one another in ways invisible to our ordinary sight. When two dust grains float close together in still air, they sometimes drift toward each other, drawn by the faintest electrostatic attraction, their surfaces bearing tiny charges accumulated through friction with air molecules or contact with other surfaces. This gentle magnetism between particles happens constantly, silently, creating temporary partnerships that last only until a breath of air separates them again. The attraction is so delicate that it cannot overcome even the slightest movement. Yet in perfectly calm conditions, dust particles slowly gather into loose, airy clusters that hang suspended like microscopic clouds within clouds. These formations have no weight to speak of, no density that matters, just the softest tendency toward togetherness, a physical preference so mild it feels almost like choice. In the upper atmosphere, far above where weather happens, dust particles from volcanic eruptions can remain suspended for years, circling the globe in stratospheric currents that move with the patience of deep ocean streams. These high-altitude particles are so fine that gravity barely notices them, and the air at that altitude is so thin that they encounter almost no resistance, drifting along pathways determined by temperature differences and the rotation of the Earth itself. A single particle from a volcanic eruption in one hemisphere might take 18 months to drift across the equator, riding invisible rivers of air that flow according to principles of physics so elegant they seem choreographed. During this long journey, the particle witnesses thousands of sunrises from above, each one tinting it with light that is not yet scattered through the lower atmosphere. These traveling specks gradually settle, descending through layers of increasingly dense air, taking months to fall from the stratosphere to the surface, spreading the chemical signature of their origin across continents and oceans. The dust that accumulates in the corners of rooms follows patterns determined by air circulation, and these patterns remain remarkably stable over time. In any given room, the same corners tend to collect dust week after week because air currents consistently deposit particles in those locations, creating what scientists call deposition zones. These zones form where moving air slows down due to friction with walls and furniture, losing the energy needed to keep particles suspended. The dust settles in soft, even layers, building up so gradually that the process is invisible, yet so consistently that you could predict which surfaces will be dustiest based purely on airflow patterns. This predictability reveals something soothing about dust. It is not random or chaotic, but follows reliable physical principles, responding to forces in ways that can be understood and anticipated. The corners that gather dust are simply places where air comes to rest, where the constant motion of the atmosphere pauses for a moment before resuming its endless circulation. Beneath the ocean, on the deep seafloor where no light penetrates and pressure is immense, dust from the continent settles in layers so undisturbed that they preserve a record of atmospheric conditions going back millions of years. This marine dust, carried to sea by winds and deposited onto the water surface, sinks slowly through thousands of meters of ocean, taking weeks or months to reach the bottom. Once there, it becomes part of the sediment, mixing with the remains of microscopic marine organisms and particles of volcanic origin. Scientists can extract cores of this sediment and read them like books, identifying layers of dust from ancient droughts, volcanic eruptions, and even meteor impacts. Each layer represents a moment in Earth's atmospheric history, preserved in perfect stillness under the weight of the ocean. The dust remembers what the air was like when it fell, carrying information forward through time in its chemical composition and mineral structure. In indoor environments, dust particles are constantly being redistributed by thermal currents created by temperature differences within a room. Warm air rises from radiators, sunlit surfaces, and electronic devices, carrying dust upward, while cooler air descends, bringing particles back down in a gentle, continuous cycle. This thermal circulation happens too slowly to feel, but it keeps dust in motion throughout the day, preventing it from settling completely until nighttime when temperatures stabilize. During the quiet hours after midnight, when heating systems rest and no sunlight warms the floors, the air in a room becomes remarkably still, and dust settles more completely than at any other time. By dawn, surfaces have accumulated a fresh, even coating of particles that spent the previous day circulating overhead. This daily rhythm of rising and settling gives dust a tidal quality, as if it breathes with the house itself, rising with warmth and descending with cool. The smallest dust particles, those measuring less than 1 micrometer across, can remain airborne almost indefinitely in normal indoor conditions. These ultrafine particles are so light that even the gentlest air movement keeps them aloft, and they settle only when air becomes perfectly still or when they encounter a surface through random Brownian motion. Because they stay suspended so long, these tiny particles have the greatest chance of being inhaled but they're also the most likely to be exhaled again without depositing in the lungs, simply riding the breath back out into the room. The human respiratory system is remarkably efficient at handling these smallest particles, which pass through the airways like light through glass, too small to catch on the surfaces designed to trap larger dust. Most of these ultra-fine particles eventually settle on surfaces through electrostatic attraction rather than gravity, clinging to walls, ceilings, and the screens of electronic devices, which often carry a slight static charge. Dust from deserts has a distinctive mineral composition that allows scientists to trace its origin even after it has traveled thousands of kilometers. Saharan dust, for example, contains specific ratios of iron, calcium, and quartz that serve as a fingerprint, identifying it unmistakably even when it falls in the Amazon rainforest or the Caribbean islands. This dust carries nutrients, particularly iron and phosphorus, that are scarce in tropical soils, effectively fertilizing rainforests and ocean ecosystems far from their source. The Amazon rainforest receives an estimated 22,000 tons of phosphorus each year from Saharan dust, replacing nutrients that are otherwise washed away by heavy rains. This transcontinental nutrient transport connects ecosystems that seem entirely separate, creating invisible threads of dependency across the Atlantic Ocean. The dust that nourishes a tree in Brazil began as rock in North Africa, was ground to powder by wind and time, lifted into the atmosphere, and carried across an ocean, all without intention or awareness, simply following the physics of wind and gravity. In the polar regions, dust accumulates in ice, becoming trapped in layers that record atmospheric conditions from the distant past. Ice cores drilled from Antarctica and Greenland contain dust from every major volcanic eruption, desert expansion, and climate shift of the last 800,000 years. Scientists can see periods when the atmosphere was dustier, indicating drier, windier climates, and periods when dust levels were low, suggesting more vegetation and less exposed soil. The dust in these ice cores is so well preserved that individual particles still retain their original shape and composition, looking under a microscope exactly as they did when they fell from the sky millennia ago. Each particle is a tiny time capsule, carrying information about the world it came from, now held in frozen stillness until researchers melt the ice and release it back into the present. The way dust interacts with sound is subtle but measurable. In rooms with more dust in the air, sound waves lose slightly more energy as they travel, absorbed by the countless tiny particles suspended in the air. This effect is minimal in typical indoor environments, but in extremely dusty conditions, such as during desert storms, the absorption becomes noticeable, making sound seem muffled and distant. The dust particles vibrate microscopically in response to sound waves, converting a tiny fraction of the acoustic energy into heat through friction. This is one of many ways that dust acts as a mediator between different forms of energy, transforming motion into heat, light into scattered color, and kinetic energy into stillness. Dust is, in this sense, a great absorber and transformer, taking energy from the environment and dissipating it gently into forms that are less concentrated and more evenly distributed. Cosmic dust continues to arrive on Earth every day, and some of it is remarkably ancient, predating the formation of our solar system. These pre-solar grains, formed in the atmospheres of stars that died before the sun was born, can be identified by their unusual isotopic compositions, which differ from anything produced in our solar system. They are the oldest solid materials that humans can touch, older than the Earth itself, survivors of stellar death and rebirth. When you consider that some of the dust in your home might include these ancient grains, mixed randomly among the skin cells and fabric fibers, the boundary between the cosmic and the domestic dissolves. The universe is not separate from daily life, but mixed into it at the finest scales, quietly present in the air we move through. Dust particles in the atmosphere play a crucial role in the formation of ice crystals and clouds. Water vapor needs a surface to condense upon, and dust provides countless nucleation sites where ice can begin to form. Without dust, clouds would be less efficient at producing precipitation, and weather patterns would be fundamentally different. Each snowflake that falls from the sky formed around a tiny particle of dust, which remains at its center, invisible but essential. When the snow melts, the dust particle is released back into the environment, free to serve as a nucleation site again in some future cloud. This cycle of incorporation and release continues indefinitely, with each particle potentially contributing to countless precipitation events over its lifetime. In clean rooms used for manufacturing sensitive electronics or conducting scientific experiments, maintaining extremely low dust levels requires constant effort and sophisticated technology. Air in these rooms is filtered continuously, passing through HEPA filters that remove 99.97% of particles larger than 0.3 micrometers. Workers wear special suits that cover every inch of skin and hair, preventing the shedding of particles that would otherwise contaminate the environment. Even with these precautions, some dust remains, testament to how pervasive and persistent these particles are. The difficulty of creating truly dust-free environments reveals how natural and normal dust is in ordinary settings. Our homes, by contrast, are comfortable ecosystems where dust exists in gentle abundance, part of the lived-in quality that makes spaces feel inhabited and real. The color of dust varies depending on its composition, and this variation tells stories about where the dust came from and what it has been through. Dust with high iron content appears reddish or brown, common in regions with iron-rich soils. Dust from limestone areas tends toward white or gray, while volcanic dust is often dark gray or black due to its basaltic composition. In your own home, dust color might vary from room to room, depending on what activities occur there and what materials are present. Dust in a kitchen might have a slightly yellowish tint from cooking oils, while dust in a bedroom might be lighter, composed more heavily of textile fibers and skin cells. These subtle color variations are like fingerprints of place and activity, recording in their hues the character of the spaces they inhabit. Dust storms on Earth, while dramatic, are gentle compared to the dust events that occur on Mars, where thin atmosphere and low gravity allow dust to be lifted to extraordinary heights and remain suspended for months. Martian dust storms can engulf the entire planet, turning the sky a uniform butterscotch color and reducing sunlight to a dim glow. Yet even these planet-wide storms are, in their own way, calm and slow, building gradually over weeks and dissipating just as slowly. The dust particles themselves are fine and soft, composed largely of iron oxide, the same compound that gives rust its color. They drift in the thin Martian air with a dreamlike slowness, taking much longer to settle than they would on Earth due to the lower gravity and atmosphere pressure. If you could stand on Mars during a dust storm, you would see a world transformed into soft obscurity, all sharp edges erased, everything distant and muted. The static electricity that causes dust to cling to surfaces is the same force that makes your hair stand up after removing a wool hat or causes a spark when you touch a doorknob in winter. This electrostatic attraction occurs because dust particles and surfaces often carry opposite charges, or because a charged surface induces an opposite charge in a neutral particle, drawing it close. Once a dust particle touches a surface, it tends to stay there until physically removed, held by these weak electrical forces. This is why dust accumulates more quickly on television screens, computer monitors, and other electronic devices, which often carry static charges. The dust is not attracted to these devices for any mysterious reason, but simply because physics favors their meeting. Understanding this removes any sense of frustration about dust accumulation. It is not a failure of cleaning, but a natural consequence of electrical forces that operate constantly and inevitably. In libraries and archives, dust is both a challenge and a source of information. Old books accumulate dust that can damage paper and bindings over time, yet the dust itself can be analyzed to learn about the environment where the books were stored. Researchers have studied dust from ancient libraries and found pollen, fungal spores, textile fibers, and mineral particles that reveal details about climate, vegetation, and human activity in the past. Each library's dust is unique, a mixture that reflects its location, the materials it contains, and the people who have visited it. This dust is a kind of unintentional archive, preserving information that was never meant to be recorded, but which accumulated nonetheless through the simple passage of time and the constant settling of particles from the air. Dust in the home is often perceived as a sign of neglect, but in reality, It is a sign of life and activity. Empty and used buildings accumulate dust differently than occupied homes, with more uniform deposition and less disturbance. In a lived-in space, dust is constantly being stirred up and redistributed by movement, creating patterns that reflect how the space is used. High-traffic areas accumulate less dust because it is constantly being disturbed and carried away on shoes and clothing, while undisturbed areas collect more. This means that dust patterns can reveal which parts of a home are used most and least, creating an invisible map of daily life. Rather than something to be eliminated entirely, dust is simply part of the texture of inhabited space, a gentle accumulation that marks the passage of time between cleanings. The way dust settles on horizontal surfaces preferentially over vertical ones is due to gravity, but the difference is more pronounced than you might expect. Horizontal surfaces accumulate dust much faster because particles falling through the air inevitably encounter them, while vertical surfaces collect dust primarily through electrostatic attraction or air currents that push particles against them. This is why shelves and tables need dusting more frequently than walls. The dust that does cling to vertical surfaces tends to be finer and more electrostatically charged, while the dust on horizontal surfaces includes larger, heavier particles that settled purely due to gravity. Understanding this difference makes dusting more logical and less mysterious. You are simply working with the natural tendencies of particles in a gravitational field. Microscopic particles of plastic, now ubiquitous in household dust, have become a subject of scientific study in recent years. These microplastics come from the breakdown of larger plastic items, the shedding of synthetic fabrics, and the wear of plastic materials through use. They are remarkably durable, persisting in the environment for decades or centuries without breaking down further. In household dust, microplastics can make up a significant fraction of the total particles, especially in homes with synthetic carpets and upholstery. Despite their prevalence, these particles are inert and stable, not chemically reactive in the conditions found in homes. They simply exist, mixed among the organic and mineral particles, another component of the modern dust mixture. Their presence is a reminder of how human-made materials have become integrated into the most basic aspects of our environment, but also of how even these materials eventually break down into harmlessness, returning slowly to a kind of equilibrium with the world around them. Dust particles can carry microorganisms, including bacteria and fungal spores, which travel through the air attached to larger particles. These microorganisms are generally harmless, part of the normal microbial community that exists in all indoor environments. They contribute to the biological diversity of the home ecosystem, and most are either benign or beneficial, competing with potentially harmful species and contributing to the development of healthy immune systems, especially in children. The idea that dust is teeming with life might seem unsettling at first, but it is simply another aspect of the natural world making itself at home in human spaces. These microorganisms are not invaders but residents, adapted to indoor conditions and existing in balance with their environment. They are so small and so few in number that they have no noticeable impact on daily life, simply riding along on dust particles as those particles drift through the air. In deserts, dust plays a crucial role in cooling the surface at night. During the day, dust in the atmosphere scatters sunlight, reducing the amount of solar energy that reaches the ground. At night, that same dust traps some of the heat radiating from the surface, preventing it from escaping into space as quickly as it would under clear skies. This dual role makes dust a moderating influence on desert temperatures, reducing both the daytime highs and the nighttime lows compared to what they would be in a perfectly clear atmosphere. The result is a slightly less extreme environment, a small but meaningful softening of the harsh desert climate. This is another way that dust acts as a mediator, standing between extremes and making conditions more moderate, more livable. The dust that falls from the sky during rain, making the first drops appear slightly dirty, has often been suspended in the atmosphere for days or weeks before being washed out. Rain is an efficient cleanser of the air, removing dust particles by incorporating them into water droplets as they fall. After a rainstorm, the air is noticeably clearer, with fewer particles suspended in it, and this clarity can last for hours or days until dust levels gradually build up again. The dust that was in the air is now on the ground, mixed into the soil or washed into streams and rivers, where it becomes part of the sediment. This cycle of lifting, suspension, and deposition is one of the fundamental processes that shapes the Earth's surface, moving material from place to place, redistributing nutrients, and gradually wearing down mountains into plains. In spacecraft and space stations, dust behaves strangely due to the absence of gravity. Without a downward force to pull particles to the floor, dust floats freely until it encounters a surface or is captured by the air filtration system. Astronauts report that dust tends to accumulate near air vents and on surfaces with static charges, creating patterns that would never occur on Earth. Cleaning in microgravity requires different techniques, often involving vacuum devices that capture dust before it can drift away. The strangeness of dust behavior in space highlights how much we take gravity for granted in everyday life. On Earth, dust settles predictably and stays where it lands, creating a sense of order and stability. In space, that order is absent, and dust becomes a more chaotic, less manageable presence, a reminder of how deeply our intuitions about the physical world are shaped by the constant pull of gravity. The dust in your home includes particles from every person who has ever lived there, layers of history accumulating in corners and under furniture. Skin cells shed years ago may still be present, mixed with more recent contributions, creating a temporal mixture that spans the entire period of habitation. This means that dust is not just a snapshot of the present, but a cumulative record, a physical archive of all the days and nights that have passed in that space. There is something comforting about this continuity, the way dust preserves traces of the past without drama or emphasis, simply by existing and accumulating. It connects the present moment to all the previous moments, creating a gentle thread of continuity that runs through time. Volcanic dust, when it falls on snow or ice, darkens the surface and causes it to melt faster by reducing its albedo, or reflectivity. Darker surfaces absorb more sunlight and convert it to heat, while lighter surfaces reflect more sunlight back into space. A thin layer of volcanic dust can significantly accelerate the melting of glaciers and snowpack, with consequences for water supply and climate. This effect is subtle and often overlooked, but it demonstrates how even a small amount of dust can have large-scale impacts when it alters the energy balance of surface. The dust itself is passive, simply absorbing light according to its physical properties. Yet through this simple act, it influences processes much larger than itself. The way dust smells, or rather the way dusty places smell, is due to the complex mixture of particles and the microorganisms living among them. Old books, attics, and unused rooms have a characteristic dusty smell that comes from the breakdown of organic materials, the presence of mold spores, and the accumulation of volatile compounds released by aging paper, wood, and textiles. This smell is not unpleasant to everyone. Many people find it nostalgic and comforting, associating it with libraries, grandparents' houses, or quiet, undisturbed spaces. The smell of dust is, in a sense, the smell of time passing slowly, of materials aging gracefully, of spaces that have been left in peace. It is a gentle, subtle scent that speaks of stillness and patience. Dust devils, those small whirlwinds that form on hot days over bare ground, are made visible entirely by the dust they carry. Without dust, they would be invisible columns of rotating air, detectable only by their effects on other objects. The dust reveals the structure of the vortex, showing how air spirals upward in a tight column, driven by intense heating of the ground. Dust devils are generally harmless, short-lived phenomena, lasting only a few minutes before dissipating as the temperature gradient that created them weakens. They are playful, almost whimsical features of the landscape, dancing across fields and deserts, picking up dust and carrying it briefly skyward before releasing it again. Watching a dust devil is like watching the air itself made visible, a temporary revelation of forces that are always present but usually hidden. In caves, dust accumulates extremely slowly because there is little air movement and no wind to transport particles. The dust that does exist in caves comes primarily from the breakdown of rock, the dripping of mineral-laden water, and the occasional visitor. Some cave dust has been undisturbed for thousands of years, lying in thin layers on rock surfaces, recording the slow processes of geological change. This dust is among the most patient on Earth, settling so gradually that its accumulation is measured in geological time rather than human time. It represents the ultimate stillness, the deepest quiet, a place where even the restless motion of dust comes nearly to a halt. Pollen grains, though often considered separately from dust, are part of the household dust mixture during certain seasons. These grains are larger and more structured than most dust particles, with intricate surface patterns that vary by plant species. Under a microscope, pollen is remarkably beautiful, with spikes, ridges, and pores that serve specific functions in plant reproduction. In the air and in household dust, pollen is simply another particle, drifting and settling according to the same physical principles that govern all dust. For people with allergies, pollen is a challenging presence, but for the plants that produce it, each grain represents a carefully constructed vehicle for genetic material, designed to travel through the air and reach another flower. The fact that some pollen ends up in your home is simply a consequence of the vast numbers produced. Plants release pollen in such abundance that its spread is essentially random, blanketing everything downwind with a fine yellow dust during peak season. The silence of falling dust is one of its most remarkable qualities. Even in a perfectly quiet room, you cannot hear dust settling. It lands without sound, without impact, simply coming to rest on whatever surface it encounters. This silence is due to the tiny mass and low velocity of dust particles. They carry so little kinetic energy that their impact produces no vibration strong enough to create sound waves. In a world full of noise, the silence of dust is a small reminder that not all motion produces sound, that things can happen quietly, without announcement or fanfare. Dust settles in perfect silence, accumulating invisibly, marking time without calling attention to itself. The tiny particles that drift through museum galleries carry with them a particular kind of stillness. These spaces, designed to preserve the past, accumulate dust that arrives from visitors' clothing, from outdoor air that seeps through ventilation systems, from the slow molecular breakdown of the artifacts themselves. Conservation scientists study this museum dust with great care, analyzing its composition to understand what might be harming delicate paintings or ancient manuscripts. What they find is always a mixture, fibers from modern clothing blended with particles that match the age of the objects they protect, as if time itself were settling in layers. The dust becomes part of the archive, a secondary record of all who came to look and wonder. There is something profoundly peaceful in knowing that even in our most carefully controlled spaces, dust finds its way in, patient and persistent, connecting the preserved past with the living present. When particles settle onto the surface of still water, they create patterns that scientists call interfacial phenomena. A grain of dust touching a pond does not simply sink or float at random. Surface tension, that invisible skin created by water molecules holding hands, determines what happens next. Some particles, coated with oils or waxy substances, rest on top, dimpling the surface slightly, held up by molecular forces. Others break through and begin their slow descent. The interaction is gentle, almost ceremonial. Researchers have discovered that certain particles can actually move across water surfaces, propelled by tiny differences in surface tension, traveling slowly from one edge of a droplet to another. This microscopic navigation happens without thought or intention, purely through the physics of molecular attraction. It is a reminder that even at scales far below what we can see, movement continues, governed by rules that are both strict and graceful. The dust that accumulates in the high corners of old churches tells stories of candle smoke and incense, of breath and fabric, of centuries of quiet prayer. When restoration teams carefully remove layers of grime from medieval frescoes, they sometimes analyze what they're cleaning away. The particles contain not just soot and mineral dust, but also pollen from flowers that were brought as offerings decades ago, fibers from vestments long since turned to rags, and microscopic fragments of the stone itself, slowly weathering even indoors. Each particle arrived through its own small journey, lifted by the warmth of candles, carried on the clothing of worshippers, or drifting in through doors open to leaden summer air. The accumulation is so gradual that no single generation notices the change. Yet over centuries, the dust becomes thick enough to dim colors and obscure details. When finally cleaned, the original brightness emerges, but the removed dust itself becomes a kind of archaeological layer, a record of devotion and presence. There is comfort in this continuity, in knowing that our smallest traces remain, even when we ourselves have long since departed. Particles suspended in fog create a landscape of softness. Fog is, in essence, a cloud that has touched the ground, made of water droplets so small that they fall at an almost immeasurable rate, held aloft by the gentlest upward movements of air. When dust particles drift into fog, they often become the nuclei around which additional water condenses. The particle, perhaps a grain of sea salt or a fragment of clay, becomes wrapped in a sphere of water molecules, growing slightly heavier but also more buoyant in the humid air. This is why fog often feels cleansing, why the air after fog has passed seems fresher. The moisture has gathered particles from the air, and when the fog finally settles as dew or burns away in morning sun, it deposits those particles onto grass and leaves, onto car windshields and spider webs. The process is a gentle form of atmospheric cleaning, a slow rain that falls so softly it barely seems to fall at all. Walking through fog, you are moving through a world where particles and water are dancing together, neither quite liquid nor quite air, existing in a state of peaceful suspension. The dust in spacecraft presents unique challenges and reveals unexpected behaviors. In the microgravity of orbit, particles do not settle. They simply float, drifting on air currents created by ventilation systems, by the breath of astronauts, by the warmth of electronic equipment. Without gravity to pull them down, dust can travel freely through cabins, potentially drifting into sensitive equipment or into the eyes and lungs of crew members. Space agencies have developed special filtration systems that constantly pull air through fine meshes, capturing particles before they can accumulate. Astronauts have reported that dust in space behaves almost like a slow-motion snow globe, with particles visible in beams of sunlight, turning gently, never landing. When spacecraft return to Earth, scientists sometimes study the dust collected in filters, finding particles that include skin cells, food fragments, and fibers from clothing, but also occasionally tiny flecks of metal worn from equipment, or even particles that entered through airlocks during spacewalks. This orbital dust is a record of life away from Earth, a reminder that even in the vacuum of space, we carry our particle-producing nature with us. The relationship between dust and photography is both practical and poetic. In the early days of photography, dust was the enemy of the darkroom, settling on wet plates and negatives, creating spots and imperfections in final prints. Photographers developed elaborate rituals of cleanliness, wiping surfaces, filtering air, working in sealed rooms. Yet, dust also became a subject of photography itself. In the right light, with the right exposure, particles suspended in air become visible as tiny points of scattered light, creating atmosphere and texture in images. Photographers learned to use dust deliberately, allowing shafts of sunlight to reveal the particle-filled air of barns and cathedrals, creating images that felt tangible and alive. In digital photography, dust on camera sensors creates its own characteristic marks, small dark spots that appear in the same location on every image, until the sensor is cleaned. These spots become familiar to photographers, almost like old friends, predictable and strangely personal. The dust reminds us that photography is a physical process, that light must travel through real air, bouncing off real particles, before it can be captured and preserved. Particles in the deep ocean move according to rhythms quite different from those on land. When dust settles onto the ocean surface, it begins a journey that may take weeks or months, drifting downward through layers of water that change in temperature, pressure, and chemistry. Some particles are consumed by plankton and incorporated into biological cycles, sinking faster as part of fecal pellets or dead organisms. Others remain suspended, their descent slowed by ocean currents that move both horizontally and vertically, creating complex, three-dimensional patterns of circulation. The deepest ocean floors accumulate sediment at rates measured in millimeters per thousand years, a pace so slow it defies easy comprehension. Yet this accumulation is steady and reliable, building geological records that scientists can read like books, finding in the dust layers evidence of ancient climates, volcanic eruptions, meteor impacts, and the slow drift of continents. The particles that rest on the ocean floor, miles below the surface, exist in darkness and cold that never changes, in a realm where the concept of weather has no meaning. There is something deeply restful in imagining this quiet accumulation, this patient building of stone from dust, happening continuously in the profound stillness of the deep sea. The dust that collects on solar panels and deserts presents both a challenge and a subject of study. Solar farms in places like the Sahara or the American Southwest must contend with the constant settling of fine particles that reduce the panel's efficiency by blocking sunlight. Engineers have developed cleaning systems, some using water, others using soft brushes, or even electrostatic charges to repel particles. Yet researchers have also discovered that not all dust affects panels equally. Fine particles, surprisingly, sometimes cause less efficiency loss than expected because they scatter light in ways that can actually redirect some rays into the panel at favorable angles. The composition matters too. Silica-rich dust behaves differently than clay-rich dust, and particles that contain iron can be moved with magnetic fields. Scientists studying these effects have learned enormous amounts about particle behavior, about how dust adheres to surfaces, how it can be removed with minimal effort, and how its presence changes the interaction between light and material. The research has applications far beyond solar panels, informing everything from spacecraft design to the preservation of outdoor sculptures. In this way, the simple presence of dust drives innovation, encouraging us to understand more deeply how particles and surfaces interact. There exists a category of particles so small they are measured in nanometers, billionths of a meter, at the scale where matter begins to behave in ways that seem almost magical. Nanoparticles can pass through cell membranes, can exhibit colors that change depending on their exact size, can have strengths and conductivities far beyond what larger particles of the same material possess. These particles exist naturally, created by combustion, by volcanic activity, by the chemical reactions that occur in atmosphere and ocean. They also exist in increasing quantities as products of human technology. Engineered nanoparticles used in medicine, in electronics, in material science. When we breathe, we inhale nanoparticles constantly, most of which are trapped by the mucus in our respiratory systems and expelled or swallowed. Some, however, can penetrate deep into lung tissue, and the smallest can even enter the bloodstream. This sounds alarming, but our bodies have been dealing with nanoparticles throughout all of evolutionary history. We have defenses, repair mechanisms, ways of identifying and removing particles that don't belong. The presence of nanoparticles in our world is not new. What is new is our awareness of them, our ability to see and measure and understand what has always been there, invisible and constant. The dust in a woodworker's shop carries the scent and character of the trees it came from. Sawdust is not generic. Oak dust smells different from pine, walnut different from maple. Each species has its own chemistry, its own blend of cellulose, lignin, resins, and aromatic compounds. When wood is cut or sanded, these materials are released as fine particles that fill the air with fragrance. Woodworkers learn to recognize woods by their dust, by the way it feels between fingers, by how it behaves when swept or vacuumed. Some woods produce dust that is almost powder fine, while others create coarser particles that settle quickly. The dust is both a byproduct and a record of the work, accumulating in corners and on surfaces, coating tools and clothing. In traditional workshops, sawdust was saved and used as bedding for animals, as fuel for stoves, as a component in compressed wood products. Nothing was wasted. There is a particular satisfaction in this, in knowing that even the smallest fragments of material have value and purpose. The dust becomes part of the cycle of making, a reminder that creation always involves transformation, that to shape one thing is to release many smaller things into the world. Particles in amber offer us windows into ancient worlds. Amber is fossilized tree resin, And when that resin was still sticky and flowing millions of years ago, it trapped whatever happened to touch it: insects, plant fragments, feathers, and dust. The dust particles preserved in amber are often overlooked in favor of more dramatic inclusions, but they are equally informative. Scientists examining amber under microscopes find pollen grains that reveal what plants were growing nearby, fungal spores that indicate climate and decay processes, and mineral particles that suggest the soil composition and erosion patterns of ancient landscapes. These particles are preserved in 3 dimensions, suspended in perfect clarity, their original shapes and surface textures intact. Unlike particles compressed in sedimentary rock, amber-trapped dust has not been crushed or chemically altered. It exists almost as it did the moment it was captured, a fragment of ancient air frozen in time. Holding a piece of amber and knowing it contains particles from an atmosphere breathed by dinosaurs creates a connection across deep time, a tangible link to worlds that existed long before humans, long before mammals, in eras when the very composition of air was different from what we know. The way dust interacts with static electricity in dry environments creates small mysteries we encounter daily. In winter, when indoor air is heated and humidity drops, particles become more likely to carry electric charges. Walking across a carpet can charge your body with thousands of volts, not enough to harm, but enough to create a spark when you touch metal. Dust particles in such environments also become charged, and because like charges repel, they can actually hover near surfaces without touching, suspended by electrostatic forces. This is why dusting in winter can be frustrating. The cloth you use to wipe a surface may itself become charged, repelling particles rather than capturing them. Anti-static sprays work by making surfaces slightly conductive, allowing charges to dissipate rather than accumulate. The phenomenon is entirely harmless and actually somewhat beautiful when observed closely. In a dark room, if you shake out a blanket that has been in a dryer, you can sometimes see tiny sparks, each one a discharge of static electricity, a miniature lightning bolt created by the friction between fabric and dust. These small lights are reminders of the electrical nature of matter itself, of the fact that everything is made of charged particles, and that under the right conditions, those charges can accumulate and reveal themselves in gentle, luminous ways. Dust in theaters has a particular quality, influenced by stage lights, by the movement of performers, by the breath of audiences held in suspense. Stage lighting, especially the powerful beams used in professional productions, makes dust visible in ways that ordinary room lighting does not. The particles drift through the beams, catching light, creating visible rays that add atmosphere and depth to performances. Lighting designers sometimes use haze machines to enhance this effect deliberately, filling the air with fine droplets that scatter light beautifully. But even without artificial haze, theater air contains enough natural dust to create subtle effects. The particles come from costumes, from sets being moved, from the building itself, old theaters especially shedding flakes of plaster and paint. There is a romance to this theatrical dust, a sense that it participates in the performance, that it has witnessed countless shows and absorbed something of their energy. When a theater is dark and empty, dust settles on seats and stages, waiting patiently for the next audience, the next story to be told. The particles that make up smoke from a wood fire are complex and varied. Smoke is not a single substance, but a mixture: water vapor, gases like carbon dioxide and carbon monoxide, and countless solid particles of partially burned wood, soot, and ash. The visible part of smoke, the gray or white clouds that rise from fires, consists largely of these solid particles, each one a tiny fragment of carbon and other elements, suspended in hot air. As smoke rises and cools, particles begin to settle, falling slowly back to Earth. Some are captured by rain, others by trees and grass, and some drift for miles before finally landing. The smell of smoke, so distinctive and powerful, comes partly from gases, but also from particles small enough to enter our noses and interact with scent receptors. Wood smoke has been part of human experience for hundreds of thousands of years, since our ancestors first learned to control fire. The particles it produces are the same ones that darkened cave ceilings, that left traces in ancient hearths, that archaeologists now use to date sites and understand how people lived. There is a deep continuity in this, a connection between the smoke rising from a campfire today and the smoke that rose from fires tended by people whose languages and lives we can barely imagine, yet who are fundamentally like us, gathering around flames, watching particles rise and disappear into the night sky. In the stillness of a library after closing, dust continues its slow work. Books, for all their solidity, are constantly shedding microscopic particles. Paper is made of plant fibers, and those fibers gradually break down, releasing tiny fragments into the air. Old books, especially those printed on acidic paper, deteriorate faster, their pages becoming brittle, their edges crumbling slightly with each handling. The dust in libraries is therefore rich in cellulose, in the very substance of the books themselves. Librarians and archivists wage a constant, gentle battle against this dust, using special vacuums with soft brushes, controlling humidity and temperature to slow deterioration, storing the most fragile volumes in protective enclosures. Yet they also understand that some dust is inevitable, that books are meant to be used, and use creates particles. There's an acceptance in this, a recognition that preservation is not about stopping time, but about slowing it, about allowing materials to age gracefully rather than catastrophically. The dust in a library is, in a sense, the library's memory made physical, the accumulated traces of all the pages turned, all the knowledge sought, all the quiet hours spent in the company of words. Particles in the human bloodstream sound alarming, but in fact, our blood carries particles constantly as part of its normal function. Red blood cells are particles. White blood cells are particles. Platelets are particles. Beyond these, blood contains proteins, fats, sugars, and minerals, many of which aggregate into small clusters that could be called particles. The body is extraordinarily good at managing these, at keeping them in suspension, at preventing unwanted clumping, at filtering out what doesn't belong. The liver and spleen act as filters, removing damaged cells and foreign particles. The kidneys filter blood continuously, extracting waste while retaining what's needed. When particles that truly don't belong enter the bloodstream, whether through inhalation of ultrafine particles, through injection, or through wounds, the immune system typically identifies and removes them. Specialized cells called macrophages engulf foreign particles, breaking them down or isolating them. This system has evolved over millions of years to handle a world full of particles, a world where breathing, eating, and simply existing means constant exposure to the microscopic. Our bodies are not fragile in the face of this exposure. They are robust, adaptive, equipped with multiple layers of defense and repair. Understanding this can be deeply reassuring, a reminder that we are built for the world we inhabit, that our biology and our environment have shaped each other. The dust that settles on butterfly wings is almost never noticed by the butterflies themselves, yet it can affect their flight in subtle ways. Butterfly wings are covered in tiny scales, each one a flattened hair that overlaps with its neighbors like shingles on a roof. These scales create the colors and patterns we find so beautiful, and they also affect how air flows over the wings. When dust particles settle on wings, they nestle between scales, generally not interfering with flight. Butterflies are not meticulous cleaners like some insects. They don't groom their wings the way flies groom their bodies. Instead, they simply continue flying, and the air flowing over their wings gradually removes loose particles. The scales themselves are loosely attached and shed throughout a butterfly's life, so any dust that has settled is eventually lost along with the scales it rested upon. Researchers studying butterfly flight have found that even wings coated with pollen or dust particles perform remarkably well, the insects compensating instinctively for any changes in weight or aerodynamics. There is something touching in this resilience, in the way such delicate creatures navigate a world full of particles without apparent concern, their flight continuing gracefully despite the constant settling of the microscopic world upon them. In clean rooms, where microchips and medical devices are manufactured, the battle against dust reaches its most extreme form. These spaces are rated by the number of particles allowed per cubic meter of air, with the strictest clean rooms permitting only a few particles larger than half a micron in an entire cubic meter. Achieving this requires extraordinary measures. Workers wear full body suits that cover every hair and pore. Air is filtered through multiple stages of increasingly fine meshes, and positive air pressure keeps unfiltered air from entering when doors open. Everything brought into a clean room must be wiped down or specially packaged. Even the movements of workers are controlled, because walking creates air currents that can stir up particles, and friction between surfaces generates new ones. Yet even in these most controlled environments, particles still appear. They come from molecular breakdown of materials, from the air in workers' exhalations that escapes through suit filters, from the unavoidable fact that matter is not static at the molecular level. Clean room engineers speak of particle budgets, accepting that some contamination is inevitable and designing processes that can tolerate the particles that will, despite everything, be present. There is a kind of humility in this, an acknowledgement that absolute control is impossible, that even our most advanced technologies must make peace with dust. The particles that form frost on windows create patterns that have fascinated humans for as long as we've had glass. Frost forms when water vapor and air touches a surface cold enough to freeze it directly, without passing through a liquid phase. The ice crystals that form are influenced by tiny imperfections and particles on the glass surface, each one serving as a nucleation site where freezing begins. From these points, crystals grow outward, their shapes determined by the molecular structure of ice and by the exact conditions of temperature and humidity. The result is the intricate, branching patterns we call frost flowers or fern frost. No two quite alike. Dust particles on the window influence where frost begins and how it spreads, acting as invisible architects of visible beauty. When we look at frost patterns, we're seeing a collaboration between glass, air, water, and dust, a temporary artwork created by physics and chemistry, lasting only until the sun warms the window and the ice returns to vapor. These patterns remind us that beauty often emerges from simple rules applied to complex situations, that order and chaos can coexist, creating something neither could produce alone. Particles in caves exist in an environment of profound stillness. Deep caves, far from entrances, experience no wind, no rain, no daily temperature changes. The air in such places can remain undisturbed for years, and particles, once suspended, settle so slowly that the process is almost geological. Cave dust comes from the breakdown of rock, from water that seeps through stone carrying dissolved minerals that later precipitate as particles, and from the rare intrusions of animals or humans. In some caves, dust layers on the floor have been dated and found to contain particles from thousands of years ago, undisturbed, preserving a record of the cave's history. Speleologists, scientists who study caves, move carefully in these environments, aware that their presence stirs up dust that may take years to settle again. They document what they find and try to minimize their impact, understanding that these spaces are archives of environmental history. The stillness of cave air, the way particles hang suspended or rest undisturbed, creates an atmosphere unlike anywhere on the surface. It is a stillness that invites contemplation, a reminder that not everywhere is subject to the constant motion and change we experience in our daily lives. The dust on Mars, that distant sibling of Earth's dust, behaves in ways both familiar and strange. Martian dust is fine, rich in iron oxides that give it a reddish color, and it covers nearly everything on the planet's surface. The thin Martian atmosphere, less than 1% the pressure of Earth's, cannot support the same kinds of weather we experience. Yet dust storms on Mars can grow to envelop the entire planet, driven by temperature differences and the planet's rotation. These storms lift particles high into the atmosphere, where they can remain suspended for months, gradually settling when the winds calm. Rovers on Mars have their solar panels slowly covered by settling dust, reducing their power and eventually ending their missions, though occasionally a passing dust devil will clean the panels, granting the rovers extended life. The dust affects everything. It clogs mechanisms, coats lenses, infiltrates seals. Yet it also tells stories. By analyzing Martian dust, scientists have learned about the planet's volcanic history, about ancient water that once flowed across the surface, about chemical processes that continue today. The dust is a library of Martian history, each particle a page, and we are only beginning to learn how to read it. Thinking of dust on another world, settling in the cold, thin air under a distant sun, creates a sense of connection across the solar system. A reminder that the processes we observe on Earth are not unique, but part of patterns that extend far beyond our home. In the moments before sleep, when your breathing slows and your thoughts begin to drift, the dust in your room is settling too. The particles that were stirred by your movements during the day are gradually descending, finding resting places on floors and furniture. The air is clearing, becoming calmer, quieter. This parallel settling, your body relaxing as dust relaxes, is one of the many small synchronies that connect us to the physical world. We are not separate from the environment we inhabit. We are part of it, influencing it and influenced by it in countless subtle ways. The dust that surrounds you contains traces of you, particles you have shed, mixed with particles from the wider world, from trees and soil, from distant deserts and oceans, from the cosmos itself. You are lying in a room full of travelers, each particle with its own history, its own journey. And now, like you, they are coming to rest. There is no need to think about any of this, of course. The facts are here if you wish to hold them gently in your mind, to let them soothe you with their quiet complexity, their reassurance that the world operates according to principles that are both orderly and forgiving. But if your thoughts are already fading, if sleep is pulling you down into its soft darkness, then let these words simply wash over you, a gentle murmur of information that requires nothing from you, that asks only that you rest. The particles will continue their slow dances whether you are awake or asleep. They will settle and rise, travel and rest, transform and endure. They have been doing this since long before you were born, and they will continue long after you are gone. There is a comfort in this continuity, in being part of something so much larger and longer than a single human life. We are temporary, but the processes we participate in are ancient and ongoing. The dust connects us to deep time, to the history of the Earth and the universe, and also to the immediate present, to the room we're in, to the breath we're taking right now. As you settle into sleep, imagine the particles settling with you. Imagine the air in your room becoming stiller, clearer, the suspended dust finding its rest just as you find yours. There is no hurry, no urgency. Everything is moving at exactly the pace it should. Your heartbeat is slowing, your muscles are releasing their tension, and somewhere in the room, a particle of dust is completing its long descent from ceiling to floor, a journey that took hours, undertaken without effort or intention, simply following the gentle pull of gravity. The world is full of such quiet processes, such patient transformations. We rush through our days, but the dust reminds us that not everything moves quickly, that some of the most important processes are also the slowest. Sediment accumulating on the ocean floor, building stone, ice forming in clouds, becoming snow, particles settling through still air, finding rest. These things cannot be hurried. They unfold in their own time, according to their own nature. And so can you. There's no need to rush towards sleep, no need to force it or worry about it. Sleep will come, just as dust settles, naturally and inevitably, when conditions are right. Your job is simply to create those conditions, to lie still, to breathe slowly, to let your thoughts slow down and spread out, becoming less focused, less urgent, until they're more like dreams than thoughts, more like drifting than thinking. The dust in the air around you is invisible now in the darkness, but it is there, each particle a tiny world unto itself, with its own structure and composition, its own history and future. Some particles will remain suspended until morning, when light reveals them again. Others have already settled and will not rise again until the room is disturbed by movement and activity. They are patient. They do not mind waiting. You too can be patient with yourself, can allow rest to come in its own time. The facts and stories about dust are here if you need them, a gentle companion for your journey towards sleep. But if you have already drifted away, if these words are reaching you only as sounds without meaning, as a soft rhythm that simply marks the passage of time, then that is perfect. That is exactly as it should be. The particles are settling. The air is stilling. The night is deep and quiet. And you, like the dust, are finding your rest, your place, your peace. There is nothing more you need to do. The world will continue its slow turnings without your attention. The dust will continue its patient work, and you can simply let go, sinking into the softness that waits for you, the darkness that holds you, the sleep that is already beginning to wrap around you like a blanket, warm and safe and perfectly calm.